So we can do some calculations to get some relationships. The most common calculation is a gram to mole and a mole to number, or the reverse, number of units to moles, or two of these, But this is a typical sequence, and the two conversion factors that we use are molar mass. Molar mass is a mole of units. How much does a mole of units weigh? And that's usually on the macroscopic end of things. And so we've got the molar mass. And so let me show you what I mean by that. So for example, if we have grams and we want to go to moles, how many moles is that? We use a molar mass. The molar mass is grams per mole, but we have to invert it. And so if we use grams per mole like this converts moles to grams. And so we're going to invert the molar mass, and we'll put moles on the top and grams below. And then we can convert grams into moles. So let's say I'm going to do an example here. I know the molar mass of water is 18.02 grams per mole. And so if I have 1 drop of water, how many moles is that? Okay, so this is what I'm going to, well, actually, maybe I'll do something simpler. Let me do a simpler calculation. Let's say I have 5.00 grams of water. So this is about 5 milliliters of water, right? So if I have 5.00 grams of water, then I'm going to do this. 1 mole of water weighs 18.02 grams, because the average water molecule was 18.02 therefore the mole of average water molecules is going to weigh 18.02 grams of H2O. This is pure water. And so the grams of H2O cancel with grams of H2O, and that gives me moles of H2O. So how many moles is that? That's about 1/3, less than 1/3 of a mole. 6 grams would be about 1/3 of a mole. So 5 to about 18 is going to be 5/18, which is 0.277. 0.2777 moles. We're allowed 3 sig figs, so let's round this to 0.278 moles. But moles are a little bit abstract, and so sometimes we're interested in the number of water molecules, that is. So in 5 grams of water, how many water molecules is that? And so we can go from moles to number of units here by using Avogadro's number, N sub A. We can use Avogadro's number because a mole of anything is 6.022 times 10 to the 23rd of those. And so there are 6.022 times 10 to the 23rd units. This is to 4 sig figs per mole of units. We could also go backwards just by flipping it. If we flip this and invert it, we can go from units to moles by multiplying it by this conversion. A mole of units is 6.022 times 10 to the 23rd of those units. And this is for anything, this is not specific. And so what I can do is here, I can just add one more conversion factor here, but I don't want to do an intermediate roundoff. I should carry the digits. Actually, this is a bar over the 7, so I should carry the digits out here. And so if I could go to moles, so grams of water to moles of water, this is moles of H2O, and then moles of water to number of water molecules. And so I would just multiply this by Avogadro's number, 6.022 times 10 to the 23rd. I could do this all in one step rather than stopping for the intermediate calculation per mole. And so this would be 6.022 times 10 to the 23rd water molecules per mole of water molecules. A molecule is not the same as a mole. So I have that. I didn't clear it in my calculator, and I'm just going to times it by 6.022 times 10 to the 23rd. And so I should be able to get this to 4 sig figs, 3 sig figs, 1.672 times 10 to the 23rd H2O molecules, which is going to be, basically this is going to be 167 billion trillion water molecules. 167 billion trillion water molecules. If I got that right. So 167 billion trillion. That's a lot. H2O molecules. A billion, I should be able to figure this out. A billion's 10 to the 9th. A trillion's 10 to the 12th. So 10 to the 9th, 9 plus 12 is 21, 22, 23. So billion trillion is correct. H2O molecules. That's huge. What about one drop of water? And so let's do one drop of water. So if I have one drop of water, how many water molecules are there? So I'm going to go one drop of water, and then I'm going to use this conversion factor. If you remember this conversion factor, there is approximately 1 milliliter in 20 drops, or 20 drops makes about 1 milliliter. This sig fig, this is not so precise, you know. This is like 1 or 2 sig figs, and that's it. Can't do much more than that. And then we know the density of water. The density of water is 1.0. So we know there's 1.0 grams of water per 1 milliliter of water. That's the density. This is just for water. We could go 1.00, you know, depends on the temperature. And then we're going to go from grams to moles. So we'll use this one. A mole, the molar mass, inverted. 1 mole of H2O molecules weighs 18.02 grams. H2O. And so drops cancel, milliliters cancel, grams cancel. That leaves me with moles of water. And then we're going to use Avogadro's number, 6.022 times 10 to the 23rd H2O molecules in a mole. In a mole. And so how many molecules in a drop? And so I'm going to do, let's do this. I'm going to take 6.022 times 10 to the 23rd divided by 20 divided by 1802. And that should do it. 1.67. How many? I'm allowed about 1 sig fig here. 1.67 times 10 to the 21. 1 point let's say 1 point, about 2. Let's just go with that. If I call this 1 or 2 sig figs here, it comes out to about 2 times 10 to the 21st. So let's do that. A trillion's 10 to the 12th. A billion is 10 to the 9th. So 9 plus 12 is 21. So that takes care of that there. And so this comes out to 2 billion trillion. 2 billion trillion water molecules in a drop. So can we count the number of water molecules one by one? No. You know, you wouldn't be able to count them one by one. We could do a dimensional analysis. If you can count, let's say 5 water molecules per second, you know how many seconds would it take? It'd take many lifetimes to do it. I think, you know, billion trillion. How many seconds are there in 100 years? You know, we'll figure that out. Are there more than 1 billion trillion seconds in 100 years? So we could just do that dimensional analysis. How many seconds are there? So this will be just a side calculation. And so 100 years. And then we're going to convert that into days. And then we're going to convert that into hours. And then we're going to convert that into seconds. So 100 years times 365 days per year times 24 hours per day times 60 minutes per hour times 60 seconds per minute. I needed one more, hours to minutes and then minutes to seconds. And it comes out to 369. 3.1536 billion seconds. So in order to count to 2 billion trillion, you'd have to count more than 1 billion. You'd have to count more than 1 billion water molecules a second in order to do that in 100 years with no breaks. So it's impossible to count. So one sig, yeah, this one's going to have one. Actually, this one's probably good to 2 sig figs. 20 drops per milliliter. And so really, I probably should have 2 sig figs here, 1.7 rather than 2. It says 20 drops, isn't so accurate there. I mean, it's okay. And so that's a good rule, but it's off a little bit. Okay, let's move on. So that's a typical calculation. Gram to mole conversion is very common. And number of units. So going to the left to right or right to left here, either way, do it. Now, what we have is the atom or mole composition, what I call atom or mole composition or dozen composition, whatever you want to call it. And so let's look at H2O. H2O, if I look at it, 2 hydrogens, 1 oxygen. 2 dozen hydrogens, 1 dozen oxygen. 2 moles of hydrogen, 1 mole of oxygen. It's atom or mole composition. So we call it the atom/mole composition. Dozen isn't very useful for us, so we don't use dozens. We either count it in atoms or moles of atoms. Typically we count it in moles of atoms. And so normally we'd say 2 moles of hydrogen atoms, 1 mole of oxygen atoms. 2 moles would be 12 times 10 to the 23rd. 1 mole would be 6 times 10 to the 23rd. So we can see it that way. And this makes sense to us. Atom or mole composition. Well, there are 3 atoms total. So 2 out of the 3 are hydrogen. It's 2/3 hydrogen, 1/3 oxygen by atom or mole. In other words, it's going to be 66.7% hydrogen, and it's going to be 33.3% oxygen. That's what we're going to get. Something like that. So 1/3 oxygen, 2/3 hydrogen. Percent hydrogen, percent oxygen. Now, alternatively, we could do mass composition. When we do a mass composition, what's the total mass? Well, this is 3 atoms total, 3 atoms. And so if we do the atom composition and we times it by 100, we get the, atom percent. Well, H2O weighs 18.02. So that's the total mass, U or grams. Depends. You use moles and it's grams. And so out of that, it doesn't matter what we use, so I'll leave it blank here. Out of that, how much is hydrogen? Well, hydrogen is, it's going to be 1.0808 times 2. So we have 2 hydrogens in there. And so this would be the amount of hydrogen, U or grams, divided by 18.02 U or grams H2O. And then we take it times it 100 by 100%. That gives us the percent by mass composition. And so in other words, what I'm doing here is this: the percent hydrogen by mass equals the mass of hydrogen, which is 2 times, because I have 2 hydrogen atoms, 2 times 1.008 over the total mass. Total mass is how much the water molecule weighs, 18.0 U, 2 U times 100%. It's the same thing here, but I skipped it. And so let's go ahead and calculate it. And when we calculate that, it's going to be 2.016 divided by 1802 times 100. 11.187. So I'm allowed 4 sig figs. 11.187% hydrogen. This is by mass. By atom, it's 66.7% hydrogen by atom. And so, but hydrogen atoms don't weigh much. And so that's why by mass it's mostly oxygen. By atom, it's mostly hydrogen. Let's do the percent oxygen by mass. The percent oxygen by mass, how much does an oxygen weigh? An average oxygen weighs 16.020 U or grams, divided by the total mass, 18.02 U or grams times 100%. So this is oxygen, this is H2O. You know, or we take the difference, 11.187 minus 100. And that's the other way we can do it, because they got to add up to 100. And so 88.81, 812%. Does this add up? No, it's a little bit of rounding there. I didn't carry all the digits, but it should add up to 100. This is oxygen by mass. So when we look at a formula is an atom ratio. If we did a mass ratio, it'd look very funny. It'd be H11.187, O 88.812. We do not do mass ratios. We do atom ratios, H2O. You know, atom ratios are much more descriptive. You know, if I did H11.18, you know, it's not very descriptive as to what's going on. Structurally, you can't really see what's going on. Atom ratios are the thing to do here. Atom ratios, not mass ratios. Here, but you know, we're interested in the mass composition here. So if I have 100 grams of water, I have 11.187 grams of hydrogen. And so this is how I use these numbers. I can use these numbers like this. 100 grams of water contains 11.187 grams of hydrogen. This is just atomic hydrogen, because we don't have hydrogen gas. Even though this is H2, it's not hydrogen gas. It's hydrogen atoms bonded to an oxygen. And we're going to have 88.812 grams of oxygen. And we could get conversion factors for this. The conversion factors that we'd use here for this might be something like this. 11.187 grams of H for every for every 100 grams of H2O. Something like that, you know, etc. So we could use those to figure out how many grams of a particular element that we have in the sample. This would be like the chlorinating solution. The chlorinating solution is going to consist of chlorinating compound, and we'd like to know, you know, how much chlorine is in that chlorinating compound in terms of grams. So we could do something like that. This is a percent by mass composition. Now, how do you determine the compositions, whether it's an atom composition or a mass composition? How do we determine the compositions? Well, it turns out there are different techniques that we can use to determine compositions. And determination of composition, the techniques all fall under the umbrella of elemental analysis. We figure out, you know, what elements are present and in what quantities. Once we figure out what elements are present in what quantities, then we can get the atom ratio, the formula. But typically when we do elemental analysis, we get the mass ratio first and then get the atom ratio second. There are many methods. One example is the combustion analysis, determination of empirical formula. There's something called the empirical formula, and there's something called the molecular formula. Let me do it quick. Empirical is the simplest whole number ratio. Do a different color here. Simplest ratio. Molecular formula is the ratio found in the molecule. So let's look at H2O. H2O this is the simplest ratio, and this is the molecular ratio. They're the same. The empirical formula and molecular formula are the same thing. However, for H2O2, H2O2 is hydrogen peroxide. And H2O2, this is not the simplest. The simplest ratio for H2O2 is HO. And H2O2 would be its molecular formula. One molecule of H2O2 has two hydrogens and an oxygen bonded to it. This would be half a molecule here. You'd have to break it in half to get HO. And so here they're different. In hydrogen peroxide, they're different, right? In water, they're the same thing. So what we have here is we have this one. This is a carbon hydrogen CXHY. We call it a hydrocarbon. It could be more complicated. There could be oxygen and other elements in there, and we could still do this combustion analysis. But if we take a hydrocarbon, a compound that contains hydrogen and a compound that contains carbon, these are combustible. These are flammable, so we can burn it. If we burn it, we're going to form CO2 and water. So we combust it in O2, oxygen, and we form CO2 and H2O. And what happens here is that all the carbon in the original compound, ends up in CO2. And all the hydrogen in the original compound ends up in, so all the hydrogen in the original compound ends up in H2O. And so we can keep track of it. And so this is an H2O absorber, this is a CO2 absorber. We can capture all the CO2 that's generated and capture it here and weigh this. And the same thing, all the water that's generated containing all the hydrogen is captured here, and we could weigh this. And by weighing these, we can figure out how many grams of CO2 forms and how many grams of H2O form. So let's watch this video here for a moment.
A combustion reaction of a compound with oxygen forms water and carbon dioxide. The water, represented as blue speckles, is trapped in one chamber, and the carbon dioxide, represented by white speckles, is trapped in a separate chamber. The mass gain of each chamber can be used to calculate the empirical formula of the compound.
So here we don't know how many carbons we have, what the ratio is, the atom ratio. You know, the composition is given by the atom ratio. So I call it X, CXHY. We're trying to figure out what X is and what Y is, you know, and we can do that. We can do that with a process called stoichiometry. Stoichiometry is just quantity relationships. Quantity relationships. And so we'll do that for this particular problem, you know, to try to figure out what the empirical formula is for this. The molecular formula, we need a little bit more information to figure that out. So this is just going to be for the empirical formula right now. So let's take a look at number 74. This is from your book. A researcher took 27.37 grams of a certain compound containing carbon and hydrogen. And so right now we have some, you know, compound here. And this is CXHY. And we have a total of 27.37 grams. But we don't know what its composition is. But we do know it's carbon and hydrogen, and that's it. And burned it completely. And so we're going to add what we call excess. You know, excess means more than enough oxygen. And so this should be complete combustion. And when this burns, all the carbon is going to end up in CO2 gas, and all the hydrogen is going to end up in H2O liquid. And so we can track that. All of the carbon was changed to 85.9 grams of CO2. And so when you burn this, this yielded 85.9 grams of CO2. And all the hydrogen was changed to 35.5 grams of H2O. And so we end up with 35.5 grams of H2O. It seems like the masses don't add up, but the masses do add up. You know, this plus the oxygen, the total mass of the reactants is equal to the total mass of the product. So it's called law of conservation of mass. All right, that's just the oxygens, you know, change things. Now, how many grams of carbon did we have in there to begin with? Well, there are different ways of doing this. This is the way I do this stoichiometrically. Your book might do it a little bit different, but it doesn't really matter. Okay, so we're going to first figure out carbon. And so we go with 85.9 grams of CO2. And then what I'm going to do is I'm going to convert that into moles of CO2. Right? And so what's the mass of carbon is 1201 is the average mass. And then I have two oxygens. Each oxygen is 1600, so it comes out to 3200. So it comes out to 44.01 for CO2. So an average CO2 molecule weighs 44.01 U. A mole of CO2 average molecules weighs 44.01 grams. And so what I'm going to do here is I'm going to go 1 mole of CO2 weighs 44.01 grams of CO2. So the grams of CO2 cancels out. That leaves me with moles of CO2. Now I'm going to use the formula ratio here. For every carbon, we have, for every CO2, we have 1 carbon. And so what I can say is that I have 1 mole of carbon atoms, or 1 dozen carbon atoms for every 1 mole of CO2. So every CO2 has 1 carbon. Okay, and so that's what I'm going to do here. I'm going to go 1 mole of carbon for every 1 mole of CO2. Now, a chemical formula is a mole ratio. Is a mole ratio. So I'm going to stop here, mole or atom ratio, or atom. So I stop here at moles of carbon because I'm going to take a ratio. All right, the hydrogens, we're going to do the same thing. For hydrogen, we had 35.5 grams of water. Here. Okay. Okay, sorry about that. All right, so here I got 35.5 grams of water, and I calculated the molar mass of water earlier. 1 mole of water weighs 18.02 grams. And so the grams of water cancels here. And then I have 2 moles of hydrogen atoms for every 1 mole of water molecules. And so the moles of water cancels here, and that leaves me with moles of hydrogen. And so what I want to do is I want to get a mole ratio, and that's going to be my formula. A chemical formula is a mole ratio or atom ratio. And so let's calculate how many moles of carbon I have. And so the moles of carbon that I have is 85.9 divided by 44.01 equals 1.95. So I got 1.95. How many sig figs? 3. So let's carry 1 extra, 1.951 moles of carbon. Okay, then let's go to water. 35.5 divided by 18.02 times 2. This is going to be 3.940 moles. And so the ratio, the mole ratio I have here is carbon 1.951, oxygen 3.940. Well, if you recall, the law of multiple proportion says we have to have whole numbers. And so we have 2 choices. We could round this, you know, to 2 and round this to 4. But before we do this, we do this. We divide by the smallest number. And so this is going to be carbon 1.951 divided by 1.951. Oxygen 3.940 divided by 1.951. This is going to give us a ratio that's simpler. So carbon is going to be 1.00 sub 0, you know, Oxygen will be 3.94. 3.94 divided by 1.95, 1. And then it comes out to 2.019. And so we're going to simplify this into the simplest whole number ratio, CO2 is what we get. Oops, what am I doing? H, this is supposed to be H. Sorry, not O. I was thinking something else. This is H, hydrogen, not oxygen. I don't know. I'm not going to erase it. I'm just going to scribble over it, sorry. CH2. So this is what we call the empirical formula, EF. Now, we need to get the molecular formula. And so if that's the empirical formula, then these are our choices for molecular formula. And so let's write that over here since I don't have that much space. Okay, so if the empirical formula is this, then what are our choices for the molecular formula? Then the molecular formula is going to be this. It's going to be CH2, that is, the empirical formula is the same as the molecular formula. Or it could be C2H4, or it could be 3, C3H6, or it could be 4, C4H8, or, gosh, I keep screwing this up, C5H10, C6H12, etc. It could be any one of these. Now, which one is it? Which one it is we need a little bit more information. We need to weigh a molecule. Do you know how you can weigh a single molecule? You can't weigh a single molecule in balance, but you weigh a molecule in a mass spectrometer. We can weigh single molecules in a mass spectrometer. There are some complications with that because sometimes the molecules break apart in mass spectrometer, and we're weighing fragments of molecules, but there are ways to minimize the fragmentation, and you could weigh actual molecules in a mass spectrometer. So if we know how much a molecule weighs, then all of these weigh different mass. This would weigh the empirical mass. This would double the empirical mass. This would be triple, quadruple, 5 times, 6 times, whatever, the empirical mass. And so we calculated the empirical formula, but we want the molecular formula. And so let's look at this slide here. Determination of the molecular formula from the empirical formula in molecular or molar mass. So when we send out a sample for elemental analysis, this is typically what we get back. So let me show you. That was combustion analysis that we just did. And so if we send out a sample from elemental analysis, and so we send it out to a lab that specializes in doing elemental analysis. From elemental analysis, we get the results. Your compound contains 31.42% sulfur, 31.35% oxygen. This is O, not O2. And then 37.23% F, not F2. These are atoms bonded into a molecule. And so what we do here is this. We assume 100 grams. 100 grams. And then we get the grams of each. Grams of sulfur, grams of oxygen, grams of fluorine. And then we convert that to moles. Moles using the molar mass. We'll have to flip over the molar mass. So 1 over the molar mass. We'll get the moles of sulfur, moles of oxygen, moles of fluorine. And then we get the simplest ratio. Simplest ratio, simplest whole number ratio. Whole number ratio is what we call the empirical formula. And then from the empirical formula, we weigh the molecule. And so we use the molecular mass to tell us which one it is to get the molecular formula. So we'll go through the steps here. So the first step is to assume a 100 gram sample. If I have a 100 gram sample, then 31.42% of that 100 grams is sulfur. And so what that means is I'm going to have 31.42 grams of sulfur, 31.35 grams of oxygen, and 37.23 grams of fluorine. Okay, then I'm going to convert it to moles. And so 1 mole of sulfur weighs 32.07 grams. I get this from the periodic table. And then 1 mole of oxygen, average oxygen mole weight, atoms weighs 16.00 grams of oxygen. And then fluorine, I have to look that up. Well, actually, I already know the number's 19.00, but let's take a look and confirm that for fluorine. For fluorine, we look at the periodic table. What we're going to do is we're going to go 2 decimal places. And so we've got to round that up. And so it's going to come out to 19.00 here. Okay. So let's go back to this. So 1 mole of fluorine weighs 19.00 grams, the average atoms. So 1 mole of fluorine weighs 19.00 grams. Okay, so that's going to give us the moles, and we want the mole ratio. And so let's go ahead and do this. 31.42 divided by 32.07. 0.97. We're allowed 4 sig figs. So I'm going to go 0.97973. 97.973 moles of sulfur. Okay, 31.35 divided by 16. This is going to give me 1.959. 1.959. Let's go one more digit. 3 moles of oxygen. And then fluorine is 37.23 divided by 19. And that gives me 1.9594 moles of fluorine. Now this doesn't look like simple whole numbers. And so the way we get the simple whole numbers is we divide by the smallest. And the smallest here is divide by the smallest is 0.97973. And so if we divide by the smallest, we're going to get 1.00 to 4 sig figs, 1.000 moles of sulfur. Okay, now we're going to divide by the smallest here. And so this is going to equal 1.9593 divided by 0.97973. You know, dividing by the smallest, the 0.97973 divided by 0.97973 is just 1. And so let's take 1.9593 divided by the smallest, 0.97973, and that's going to give me 1.99. I'm allowed 4 sig figs, 1.9998 moles of oxygen. Okay, now dividing this one by the smallest is 1.9594 divided by 0.97973. And so 1.9594 divided by 0.97973. Okay, and this is going to come out to 1.9999 moles of fluorine. And so now what we're going to do is we're just going to round it. And so I'll just round this S. How should I write this? I'll just write it in the same order they gave us, SO. S1, O2. So this is going to be 1, and this is going to be 2. This is going to be 2. SO2F2. SO2F2. This is the empirical formula. Now, how much does this unit weigh? Okay, so when we get the empirical formula, we're going to get the empirical mass first. And we're going to figure out how much does the empirical unit weigh. And so let's do that here. So I'm going to tabulate the mass here of this. And so I have one sulfur is at 3207, and then I have two oxygens. 2 times 16 is 3200. And then I have two fluorines. 2 times 19 is 3800. And so that comes out to 7, 0, 10, 12, 9, 10, 102. And so this unit here weighs 102.07 U. Okay, then they took this compound and fed it into a mass spectrometer. When they feed it into the mass spectrometer, they see that the molecule itself weighs 102.1 U grams per mole or U per molecule. And so this is 102.1 U per molecule. And so we see that this empirical unit here weighs the same amount as a molecule this does. And so they must be the same. So this is equal to the molecular formula. It's got to be some ratio. It could be double. Let's say they weighed a molecule and it came out to 204 U. Then we have to double everything. Because a molecule, single molecule of this would have 2 sulfurs, 4 oxygens, and 4 fluorines. Make sure I'm recording, yeah. Okay, so what I want to do here is, this is a short chapter, so let's take a look at some of the problems in this chapter. Okay, just had to go for a moment there. But let's take a look at the problems here. Okay, how many atoms of each element are in the formula unit of ammonium nitrate? So ammonium, we got to look at the, or aluminum, sorry, aluminum nitrate. I'm looking at this one. Aluminum is Al3+, nitrate is NO3-. And so we can need 3 nitrates. And so we got Al parentheses NO3, 3. So in this, we're going to have 1 aluminum and then 3 nitrogens. 3 nitrogens. That's going to come from here. And then 9 oxygens because we have 3 nitrates. And so 3 nitrogens here and 9 oxygens here for the 3 nitrates. 2, how many atoms of each element are in ammonium phosphate? So ammonium is NH4 plus, phosphate is a 4 oxygens and a 3 minus, PO4 3 minus. Make sure you get these down off the periodic table. And so we'll need how many ammoniums? We're going to need 3 ammoniums. And so this is going to be NH4 parentheses 3 PO4. And so if we have 3 ammoniums, there's 3 nitrogens. So 3 nitrogens and then 12 hydrogens. 4 plus 4 plus 4 is 12. And then 1 phosphorus and then 4 oxygens. That would be that. Why is it proper to speak of molecular mass of water, but not the molecular mass of sodium nitrate? Reason is because water forms molecules and sodium nitrate forms lattices. And if you have lattices aren't made up of individual molecules. Sodium nitrate is an ionic compound which forms lattices, not molecules. Molecules can also form lattices, but they're lattices of molecules, like ice. And it's a little bit different though. It may be said that because atomic, molecular, and formula masses are all based on carbon-12, they are conceptually alike. What then are their differences? All of these are, atomic mass is U per atom. There's a pen here. Atomic mass is U per atom. Molecular mass is U per molecule, a single molecule. This is a single atom. This is a single a molecule. And formula mass is U per formula unit. Because some things don't form single atoms, some things don't form single molecules, some things form a formula unit like sodium nitrate. Sodium nitrate doesn't form molecules and it's not atoms, therefore we call it a formula unit. In what units are atomic, molecular, and formula mass expressed? Well, these are the units here, U. Find the formula mass of each of the following substances. So this one, we just want to see. We just look up lithium on the periodic table and chlorine. Chlorine's 35.45. 35.45 for chlorine. Lithium, look it up on the periodic table, 6.94. These are numbers from the periodic table, add them together. Lithium chloride is LiCl. First, we have to get the right formula. If you don't get the right formula, you can't answer these questions. And so we got to know the formulas. Aluminum carbonate. Aluminum is 3+, carbonate is 2-. And so here we're going to need 2 aluminums and 3 carbonates. 2 aluminums and 3 carbonates to balance it out. That is, if I take 2 aluminums, it's 6+, and then 3 carbonates is 6-. And so it balances out. And so what I got to do is I got to look up aluminum on the periodic table and multiply by 2, and then I got 2 carbons and then 6 oxygens. Carbon's 1201, oxygen is 16. You know, there's certain ones that you want to know because they'll speed things up. Aluminum's 2698 off the periodic table. We got 2 of those. And then carbon's 1201. We want to memorize that eventually. 3 of those and 9 at 1600, which is oxygen. It gives me 233.99. Ammonium sulfate. I want to make sure we get the formula for ammonium sulfate correct. In fact, let's get all the formulas here first and then figure it out. Ammonium sulfate is NH4. We need 2 of these because the sulfate is a 2-. This is butane, C4H10. Silver nitrate, silver is a +1, nitrate's a -1, so that balances out nicely. Manganese 4, okay, manganese is a 4+, oxide's a 2-, so we're gonna need 2 oxides for every manganese, like this. Zinc phosphate, zinc is a 2+, phosphate is a 3-, and so we'll need 3 zincs and 2 phosphates to balance this out, like that. And so here, this means 2 nitrogens at 1401 times 2 is 28. Actually, let's just do this. We need practice doing this. So 2 nitrogens is 2 times 1401, which is going to give us 2802. And then we have 8 hydrogens. Is 8 times 101 is 808. And then we have 1 sulfur, which is 3207. So this is 3207. And then 4 oxygens. Oxygen 16, so 4 of those would be 64. Actually, I should do 4 times 16.00. 4 times 16.00 is 64.00. And so just adding up 15, 17, then 16, 20, 22, and then 10, 13, 132, 17, if I didn't make any mistakes with the addition. So this is ammonium sulfate. Let's check it. 132.14. It's slightly off because they might have used slightly different masses. Which one did they use? This one is different. This one they didn't have to go, you know, their number is actually better than mine because I used 101. But you don't need 1008 because what happens is it throws your decimal places off. We want to keep all the molar masses to 2 decimal places. So just make sure we get 2 decimal places in the molar masses and then we're set, okay? We're set. These molar masses are a little bit tedious and they aren't that difficult to do once you've done a bunch of them. But some of these are helpful for knowing, for helping you memorize certain molar masses like carbon. Carbon's so common. And so that's 4 times 1201. That's carbon. And so this gives us 48.04. This carbon. And then hydrogen. Hydrogen's easy. We have 10 times 101, which is going to be 10.10. Basically, or, you know, we aren't allowed that many sig figs, but we're just going to carry it. This one is a trouble, but it's okay. It's going to come out to 58.14 U. Theirs is going to be a little different because they use 1008. You don't have to use 1008. Just use 101 if you want. Let's see what they did. Yeah, it's 1201, but they use 1008. They get 58.12. We get 58.14. This is within rounding error. Their answer is a little bit more accurate. However, you know, it requires more time to do it, a little bit more time to do it. You know, silver nitrate consists of 1 silver, 1 nitrogen, 3 oxygens. Silver is heavy, 107.9 off the periodic table. I would go 2 decimal places. They only want 1 decimal place here. I go 2 decimal places on everything. Nitrogen's 1401, oxygen 1600, 169.9. I would have gotten this to 2 decimal places, 5 sig figs. Manganese, look that up on the periodic table. We have 2 oxygens, 32. We add those up. Zinc phosphate, we had 2 zincs, or 3 zincs, sorry. 2 phosphorus, 8 oxygens. We add those up. Here, we just got to make sure we get the right formula. Nitrogen trifluorides, NF3, barium chlorides, BaCl2, lead 2 phosphate. This one's a bit more tricky. Let's write that one out. Lead 2, there's 2 ways. I'm going to do this is the second way of doing it. We have too much negative charge, add another lead. Now we have too much positive charge, add another phosphate. Now we have too much negative charge, add another lead. And now it's balanced, 6 plus, 6 minus. So this is PB3, PO4, 2. 3 leads, 2 phosphorus, 8 oxygens. Add up those masses and we're done. Let's continue on here. Sulfur trioxide, 1 sulfur, 3 oxygens. Do that. Sulfur is 3207, oxygen 16. They're using 3206 for their sulfur, so it's a little slightly off. This depends on which periodic table you use and how they round it. Plus those three oxygens here. Hydrogen fluoride, that should be easy. HF is, H is 1, F is 1 H atom, 1 F. H is 101, F is 1900, so 2001 U. When HF reacts with SBF5, it forms a superacid. Superacids are even stronger than the strong acids I had mentioned. This is a superacid, HSBF6 superacid. Superacids are important in certain chemical processes. Nitrogen dioxide, how much does this weigh? Well, 1 nitrogen is 1401 plus 2 oxygens is 32. So we can do that pretty quick here. Once you start doing a lot of these, they become much faster. 1401 for that, 2 oxygens, 3200, altogether 4601 U, or grams per mole. U per molecule or grams per mole molecules. Okay, let's go on here. Dichlorine monoxide. Dichlorine monoxide is a bleaching agent. You know, it's because the chlorine's unhappy in this. And so let's look at dichlorine monoxide. Dichlorine monoxide is going to be Cl2O. Oxygen gets its normal charge, -2. That means each Cl is plus. And so this is a bleaching agent. It's not so happy. It wants electrons. Cl likes to be -1. And so what is this? Well, 2 chlorines, that's 2 times 35.45, which is going to be 70.90, plus the 16 from the oxygen. And so this is going to be 8690 U for that molecule, or 8690 grams per mole of these molecules. Is it 430? What do quantities representing 1 mole of iron atoms and 1 mole of ammonium molecules have in common? They're both going to be 6.022 times 10 to the 23rd. This would be 6.022 times 10 to the 23rd atoms. This would be 6.022 times 10 to the 23rd molecules. And so they're different because one describes the number of atoms, the other describes the number of molecules. Okay. Explain what the term mole means. A mole is the counting unit, you know, like the dozen, but it's a very big counting unit. Why is it used in chemistry? Because we need to count huge quantities, you know. If you count a dozen water molecules, you can't even see that. And so the other question that comes up is, why is it a strange number? It's a strange number because it's defined based on carbon-12. Is a mole number? Yes. It's Avogadro's number. By definition, the mole is the amount of any substance that contains the same number of units as the number of atoms in exactly 12 grams of carbon-12. The definition doesn't say what that number is. Through experiment, we have found that to 3 sig figs, it's 6.02 times 10 to the 23rd. You could do it by experiment, or you could do it by calculation also, based on some experimental data. Atoms in 12 grams of carbon-12. Avogadro, it's Avogadro's number, but Avogadro didn't determine this number experimentally. Another person determined the number, I think, experimentally. And he's in your book. But we need it to 4 sig figs. To 4 sig figs is 6.022, so double 2 at the end to 4 sig figs. Give the name and value of the number associated with mole, Avogadro's number, and the value is this. Determine how many atoms, molecules, or formula units are in each of the following. Okay, 7.75 moles of methane. Just multiply that by Avogadro's number, we'll get the number of molecules. And so mole to molecule conversion. So moles cancel, leaves us with molecules using Avogadro's number. Again, this is going to be a mole to molecule conversion because we're going to carbon monoxide, CO. And so moles of carbon monoxide to molecules using Avogadro's number here. That gives us this number of molecules here. It's huge. Okay, moles of iron to atoms of iron. In this case, iron doesn't form molecules. So we're going to atoms of iron using Avogadro's number here. Moles of magnesium chloride to formula units. Magnesium chloride doesn't form single atoms and doesn't form molecules. It forms formula units. And so here, it's FU stands for formula units here. Those are moles, and that gives us the number of formula units, a lot. Formula unit you can kind of think of as a molecule, but it's not discrete, you know. That's it. How many molecules of boron trifluoride are present in 1.25 moles of this? So we just do a mole to molecule conversion, number of molecules. Here we go from molecules to moles. We invert Avogadro's number. How many moles of nitrogen dioxide are present in 7.89 molecules? So molecules to moles. How many molecules? So we do a mole to molecule conversion here. So these are just Avogadro number conversions here. Calculate the number of moles in each of the following. So here we're going from molecules to moles. We invert Avogadro's number. Molecules, cancel molecules, get moles. So this is Avogadro's number inverted. And so number of molecules to moles. Sodium atoms. So we figure out how many moles. And so this is just a number to mole. It turns out 11.6 moles of sodium atoms. How many atoms of hydrogen are present in 2.69 moles of water? Now this requires more quantitative relationships. So let's stop here and let's take a look at this calculation briefly. And so here we have 2.69 moles of H2O. 2.69 moles of H2O. Oh, question? Oh, is it break time? No. Or was that the previous break time? I don't remember. Okay, so we have that number of moles, and then what we can do is we can do this. We have two choices. One, we can go to number, so 6.022 times 10 to the 23rd H2O molecules per mole of H2O molecules. Okay, then for each molecule, so if I have one H2O molecule, then I have two H atoms. And so this gives me the number of H atoms. Or I could do this. I could do 2.69 moles of H2O. And then I could use this conversion. There are 2 moles of H atoms per 1 mole of H2O molecules. And then once I know how many moles of H atoms I can go 6.022 times 10 to the 23rd H atoms per mole of H atoms. So either one of these will give you the same answer. And so we either do a mole to number conversion and then a number to a number conversion using the formula, or we do a mole to mole conversion and then the mole to number conversion here in the formula. Okay. On to the next one here. In what way are molar mass of atoms and atomic mass the same? The number is the same, the units are different. The numbers are the same, the units are different. Molar mass grams per mole, atomic mass U per unit. How does molar mass differ from molecular mass? Molar mass is the weight in grams of a mole. The molecular mass is the weight in U for a single molecule. Find the molar mass of each of the following. So 3 carbons is 3 times 1201, 8 hydrogens, 8 times 101, 4409. The numbers we could use interchangeably, gram per mole or U per atom in that case. 6 carbons, 5 chlorines, 1 oxygen, 1 hydrogen. 6 carbons at 1201, 5 chlorines at 35.45, 1 oxygen at 1600, and 1 hydrogen at 1008 or 101 I would use. Nickel 2 phosphate, and so we need the correct formula for nickel 2 phosphate. Nickel 2 phosphate, the other way, we'll get the other way of getting nickel 2 phosphate. The other way of getting nickel 2 phosphate is nickel 2 plus phosphate. And the other way is just cross multiply. 2 phosphates, 3 nickels. So Ni3PO4 should do it. 3 nickels, 2 phosphorus, 8 oxygens. Let's do that. Let's take a look. They did here. 3 nickels off the periodic table is 5869. 2 phosphorus, 3097 off the periodic table, and 8 oxygen, 1600. And that gives us, this should be equals. It's supposed to be an equal sign, not plus. Zinc nitrate has 1 zinc and 2 nitrates. And so 1 zinc and 2 nitrates. Each nitrate has 2 nitrogen, so there's 2 nitrogens and then 3 oxygens, so 6 oxygens altogether. This is zinc nitrate here. Calculate the molar mass of each of the following. So we just need the formula. And we do the same thing. So you might go, I think I know how to do that. And so if not, then do it, you know. Find the number of moles of each substance. So we're going to gram to mole conversion. When we do gram to mole conversion, we need the molar mass. Now this is oxygen. Now this is confusing here because what's confusing about this one is we don't know, is that atomic oxygen or molecular oxygen, you know? And so is that an O or is that an O2? Well, gosh, that's hard to determine because, you know, the oxygen in here is O, but we have to assume it's O2, maybe in this case. Let's see what they did. Yeah, they assumed it's O2. And so when we do O2, there's 2 oxygens. Each oxygen weighs 1600, so it's 3200. So 1 mole of O2 molecules weighs 32 grams. Yeah, and so they just did a gram to mole conversion. If we used atomic oxygen, then it would be 1 mole of atomic oxygen per 16 grams of atomic oxygen. But here we're just going to do gram to mole conversion. So we got to calculate the molar mass of magnesium nitrate, which is this. And so we'd have to add up all the masses. And so we just do grams and cancel out grams, we're left with moles. So we invert the molar mass or flip it over and get the moles, magnesium. Okay, gram to mole conversion here. So we need the molar mass of aluminum oxide. This is the molar mass of aluminum oxide. 2 aluminums and 3 oxygens weighs 101.96. And then we just cancel out the grams, get the moles. This is ethanol here. And so gram to mole conversion of ethanol. 659 grams of ethanol. Ethanol weighs 4607, 2 carbons, 6 hydrogens. The hydrogens are split apart, so we just combine them. 6 hydrogens, 1 oxygen, 4607. Then we have ammonium carbonate. Ammonium carbonate has 2 nitrogens, 8 hydrogens, 1 carbon, 3 oxygens, and weighs 9609. So we'd have to add up all those and do a gram to mole conversion. Then lithium sulfide, 1 lithium, 1 sulfur, or not, sorry, 2 lithiums. Sulfide's 2 minus, lithium's plus 1, so 2 lithiums here. That's a molar mass, so gram to mole conversion. So we have to do the same thing. We have to get fast and good at calculating molar masses, you know, by adding up them here. This is another gram to mole conversion. You go, okay, after you do enough of these, this is good practice for nomenclature, by the way. You know, do nomenclature here. So KiO3, beryllium chloride, BeCl2, BeCl2, calculate the molar mass, nickel 2 nitrate, Ni, and then with 2 NO3s, Ni with 2 NO3s, nickels plus 2, nitrates minus 1, so that's why we need that ratio, and then we got to add them up. And so a lot of calculating molar masses, but let's skip that for right now. Now calculate the mass. So now we're going to go from moles to grams. Mole to gram conversion. once you're good, once you feel comfortable with molar masses, we can just use Wikipedia to do it for us, you know. So if we go to Wikipedia, let's say but only do this if you're good at calculating molar masses. If you're good at calculating molar masses, then let's go to acetic acid. Let's say I don't want to calculate the molar mass of acetic acid. I just want to look it up. And so that's given here. The molar mass of acetic acid is right here. I'm going to use that. 60.052 grams per mole. But acetic acid should be quick though. Acetic acid should be quick because of this. Let me show you why acetic acid should be pretty quick. Wrong. Acetic acid should be quick because we should know, you know, we got 2 carbons. For me, anything that contains carbon, hydrogen, and oxygen is quick, and nitrogen is quick. 2 carbons, it's going to be 2402. Each one's 1201. 4 hydrogens is 404. 2 oxygens is 32, you know. And so this is pretty quick for me, I think, because 06, 810, 6006, you know, 6006. Let's see if I got that right. Click here. Yeah, off just by 1 unit because, again, hydrogen, they use slightly more digits than I do. And so here we're doing mole to gram conversion. Lithium chloride, lithium's 6.9 something. Chlorine's 35.45, so we'll do that. Lithium, 6.94. Grams per mole, mole to gram conversion. Mole to gram conversion is common. Mole to gram conversion, we need the molar mass for that. The molar mass of iron 3 sulfate. Sodium acetate. There's a molar mass of sodium acetate. Mole to gram conversion here. Mole to gram conversion, lots of mole to gram conversions. Mole to gram conversions are very common. We need the molar mass. We have to know how to calculate the molar mass of these. And in order to do that, we need the correct formula. Potassium oxalate, we haven't really seen that much of that. K2C2O4 is a very common chemical. That's potassium oxalate. This is lead 2 nitrate. It's a pretty common chemical. Calculate the number of atoms, molecules, or formula units in each of these. So here we're going to calculate the number. So we're going to go gram to mole, mole to number. So gram to mole by flipping over the molar mass, and the mole to number by using Avogadro's number. So same here, gram to mole by using the molar mass inverted, and the mole to number by using Avogadro's number. This is formula units. This is also formula units here. This one would be formula units as well because this is an ionic compound. So gram to mole, mole to formula units here. That's it. This is molecules. So we'd do gram to moles and then moles to molecules using Avogadro's number here. This would also be molecules here. So this would be grams to moles and then moles to molecules here. This one would be formula units because it's a ionic compound. So grams to moles, moles to formula units here. Let's skip these, they're very similar. Here we're going to calculate the mass. So we're going to go from number of molecules to moles to grams. And so we're just going backwards. Number of molecules to moles by inverting Avogadro's numbers to grams by using the molar mass. And so we'll string together these conversion factors. Number of molecules, fluorine, this is wrong. Here. This is wrong, unfortunately. Oh, atoms, sorry. It's correct then. If they're saying atoms of fluorine, it's fine. Fluorine's normally F2. Okay, here, nickel 2 chloride, we're gonna go to formula units. So formula units to moles of formula units to grams. Formula units, and that's what we get. On a certain day, a financial website quoted a price of gold at $1,528 per troy ounce. 1 troy ounce is 31.1 grams. What is the price of a single atom of gold? And so let's let me just do something really quick in a moment. Yeah, is it break time? Yes, okay. All right, let's take a break and then I'm gonna, we'll cover these, 37, 38. Let me see how many more I have. How many more pages of this? I guess there's a lot of questions here. A lot of questions. 75. Okay, let's take a 15-minute break. We're going to start at 5:05 after this. Okay, so let me stop the recording here, pause it. Resume. All right, let's do one more problem here, and then we'll have to finish these next time. There's too many of them. Okay, so we're looking on a certain day. Okay, so we have $1,258 per troy ounce. So this is going to be a conversion factor. Let's go ahead and write that as a conversion factor here. And so two ways we can state that. That is $1,258 per ounce. This is gold, per ounce of gold, AU. Or 1 ounce of gold is going to cost you that much. Okay, they give us this one, another conversion. 1 troy ounce is 31.1 grams. What is the price of a single atom of gold, Z79? Let's see, is a troy ounce the same thing as a regular ounce? You know, how many grams? Does anybody know if a troy ounce is the same thing as a regular ounce? No, it is not. Okay, thank you, Hazard. And so how many, for a regular ounce, we don't need this here. The reason we don't need this is because of this. How many grams is 1 ounce? And so if I do 1 ounce, I should know this. 1 pound is 16 ounces. And so I'm going to go from ounces to pounds. And then I know that there are 453 453.6 grams per pound. Okay, so this is our standard conversion factor here. Okay. Thanks. So in a regular ounce, how many grams are there? And so I just want to do that. 1 divided by 16 times 453.6, 28.35. And so in a regular ounce, there are 28.35 grams. In a troy ounce, there are 31.1 grams. So a troy ounce seems to have a little more gold than a regular ounce does. And so what we're going to do here is a single atom of gold. And so that's what we're starting with here. We're going to start off with 1 gold atom here. And then we need to cancel it. Well, in order to cancel atoms, you know, individual atoms, this is the number of atoms, we should use Avogadro's number. and that is 1 mole of gold contains 6.022 times 10 to the 23rd atoms of gold. And so this would be a mole of gold atoms here. And so here the gold atoms cancel, and that leaves us with moles of gold atoms. And then I know how much a mole weighs because the molar mass is given on the periodic table. So let's just take a look at the periodic table here. Let's see, do I have the periodic table? And so I'm going to take a look at gold. 196.97. I'm going to go 2 decimal places. So 196.97. 196.97. So this is going to be 196.97 grams of gold atoms in a mole of gold atoms. Okay, so moles of gold atoms cancel moles of gold atoms. That gives me grams of gold. And then a troy ounce is a little heavier than a regular ounce. So 1 troy ounce is equivalent to 31.1 grams. It's 3 sig figs. And then finally, 1 ounce of gold, 1 troy ounce of gold is $1,258 per troy ounce of gold. And so ounces of gold, troy ounces of gold cancel, and that just leaves us with dollars. So how many dollars is 1 single gold atom? And so 196.97 times 1258. I'll just do the numerator, divided by 6.022 times 10 to the 23rd, divided by 31.1. Comes out to 1.323 times 10 to the minus 20th dollars. This is nothing. And so let's see what their answer is. It wouldn't be very useful to buy one gold atom. You couldn't even see it. It's 10 to the minus $20, but you can't see it, even though it's so cheap. And so here they took atoms, converted it to moles of atoms to grams of atoms using the molar mass. This is using Avogadro's. And then using the conversion for troy ounces to grams, and then from troy ounces to dollars here. That's what we did. Okay, that was 37. I'm going to stop here because I'm going to give some time for people to finish the blood alcohol if you want. Okay, so what I'm gonna do is let's take a look at the exam here. The exam, again, this is a take-home exam. A take-home exam means that it's open book, open book, open notes. You could search the internet if you want, but the problem is don't use conversions that you get from outside, from sources, Some of the conversions are combined. I want you to use the standard conversions that we had talked about in class, those. And so I'm going to post the exam one. Exam 1. This is going to be this chapters 1 through 6. Chapter 7 is not included on here. And the chapter 6 we're going to see over and over again because chapter 7 there's a lot of nomenclature there. This exam, this is a handout. Insert the file here. So you're welcome to print this out. You can print this out and then write it by hand, or if you have a, if you have a touch panel, you can do it that way and just write it on there. It's a combination of multiple choice questions, some nomenclature, and some calculations here. These calculations, I said, show all your work and use the conversion factors. I wanted to see how you calculate it. I don't want you just to Google these things, obviously. Okay. Total of 34 questions in multiple parts. The exam's worth 100 points. So you could either fill it out and then save it as a PDF and then upload it to Canvas, or you can print it out and then scan it as a PDF and upload it. It's not due today. I'll have it due. When do you guys want to do? Because you're going to do this outside of class time, except this, this little bit of class time will end early, maybe. Genius scan. Sunday might be a little late because I need to grade it. I was going to grade it on Sunday. How about Sunday? Let's do it Sunday well, that's all right. I'll just grade it Monday. Okay, Sunday. Turn it in Sunday before Monday morning. Okay. Was that too much time, or that's enough time? Okay, Sunday, turn it in before Monday morning. It should be, this is like an hour test, hour and a half test, okay? Roughly, if you want to time yourself, you should do that. Nomenclature, you should be fast enough. I didn't give you much time to memorize those, so it may take you a little longer to do those. But it's open book, open notes, open internet, but you shouldn't collaborate with others. This should be individual work, okay? And so just try to figure it out individually. All right, so that's exam. So what I'm gonna do is I'm gonna end it now, so you could start on the exam. Or if you want to break out into a breakout room, tell me who you want to work with or who you are working with for the blood alcohol, and then try to finish that, because the blood alcohol you're supposed to upload. I wanted to talk about the blood alcohol problem today. I'll end up talking about it maybe tomorrow, if you guys.
Professor, I have a question. I couldn't upload it through Canvas because I did it some other way and I didn't do it as a PDF, but I sent it to you as an email. I don't know if you got my email.
For the blood alcohol, or which one?
Yeah, that one.
Okay, did you do it as a picture, or you didn't do? I guess you didn't convert it into PDF, did you?
Yeah.
Do you have a smartphone?
No.
Okay, do you have a printer scanner combo at home?
No.
Oh.
I just sent you 2 pictures of the quiz.
All right. Okay.
So your email though. El Camino email.
Well, you can upload it to Canvas as well.
Okay.
You can upload pictures to Canvas. People did it. They uploaded JPEGs and other files. Depends on how you take the picture, what kind of file, what kind of camera you use to take the picture. It'll vary.
I'll try it again.
Yeah, try it. See if you could borrow just a scan using Genius Scan or something like that from another student.
Yeah, I'll try doing that again.
But if not, then yeah, you can always attach it as an email and send it to me. Worst case scenario is you can't get it uploaded on Canvas, then email it to me as an attachment. That'll work too. I just don't.
Okay.
Okay. All right. Now, if you want to do a breakout room, you could let me know privately who you're working with. That would be good, or publicly. It doesn't matter. And so if you want a breakout room, let me know, and I'll separate it out right now. So I know Crystal. Who were you working with, Crystal? Ariel, who else was in your group? You have to write these things down. You remember what I said about one person writing everything down? Make sure you write everything down. And that way, in case that person fails to turn it in, you can still turn it in, you know. And so Ariel, if you want, you could just turn it in separately. But if you know the other people in your group, let me know, and then I can check to see if they uploaded it.
Are we allowed to upload quiz 5 already?
Yeah, quiz 5. What is quiz 5 again?
The one that we did yesterday. It's
The nomenclature?
yeah, okay, I see it now.
Yeah, that's it.
Okay, I'll upload it that one today.
All right, so this will be quiz 5. Nomenclature. I forgot to write that in there. Let me just edit it. Same. Okay, so it's up now. Quiz 5, nomenclature. Quiz 1 was this one, the student info upload. It's not really a quiz.
What about for quiz 2 measurements?
Sean, Stephanie. Quiz 2 measurements, you don't upload that. I got that out of class, out of the chat board.
Okay.
Did you get a grade for that?
No.
Did you participate? That was during class. I don't know if were you present that day or?
Yes, I've been present like every day, but I just don't remember my group.
There was no group for
A
that.
group? Okay,
Yeah.
so I don't know.
That was either you. I showed you the measurement, and I asked everybody to type it into the chat, and then I went through the chat, and then saw the answers there. So
Okay,
that was a participation one, where you had to see it during the Zoom and then write it in. Actually, there were like 6 of them. I only took 4 out of 6, so you could have missed 2 of them and still gotten 4 points for that.
Okay.
There were more. I mean, it depends on how many you commented on. If you commented on at least one of them, I would have given you a point for that. But there are a whole bunch of questions I asked during the measurement one to do, not as a separate. But the quizzes, I don't know. Do I drop a quiz? I'm not sure. Probably. Got to look at the grade.
I don't think I was present this day, but like, can we still upload an answer for you, or is it too late?
For which one?
For this one right here.
Measurements?
Yes.
No, unfortunately, that one not. I know already people have been asking me for makeup quizzes. I'll probably just have one makeup quiz at the end.
Nice.
That you can do. You know, it'll just be the same quiz. It might not be exactly related. It will be, you know, a multitude of things probably. The makeup quiz. And since I can't, you know, it's too much. Could be too much work, you know, to accommodate, you know, having to do too many different quizzes, I think. And so it'll be easier just to do one at the end. Hopefully people don't miss too many of these quizzes. We have 20 quizzes. So in order to have 20 quizzes, we have to have quiz almost every day. I'll try to keep the quizzes at the end. So if you're late, you can still make it the quiz. Yeah, you don't have to go to the breakout room. Yeah, it's just optional. If you want to go to a breakout room, that's fine to finish this is for finishing the quiz. If you don't, that's it. You know, we're done for today. And so you could start on the exam. Okay. No, I haven't done the groups yet. I'm going to do the groups. I'm not up to. I need to do the grades for the quizzes, starting with the pool water. I haven't inputted those yet. Okay. Yeah, if you're done, you can leave. That's fine. You're dismissed. Unless you want to work in a breakout. If you want to work in a breakout room, let me know. for the blood alcohol if you want to work with others. You can also do that on your own as well. But class is over now. Officially, class is over. It's just optional.
I'm on the on Canvas on my phone right now, and I'm looking at the student info upload. And then I pressed on take quiz for the thing, and it says quiz instructions, and it just says question one, upload a file and choose a file. What?
Yeah.
Wait.
Okay, that one is posted on Piazza.
Oh, got it. Okay.
Yeah, just like the exam is posted on Piazza, and
Okay.
then you get it off Piazza, and then you upload it onto Canvas.
Okay. Perfect.
Okay. Okay.
Thank you.
Okay. I guess there are no breakout rooms then. Is that correct? No breakout rooms. Then that's it for class. But I'll stick around to answer any questions you guys have. So I'll keep the room open. So if you have a question, let me know. Okay. I'll keep the room open for a bit. Okay, but anyway, good luck on the test. Again, the test is going to be due before Monday morning. Like say before Monday morning, 9 a.m. or something, in case I need to print those out in the morning. Yeah, for the test, you can print it out, Diana, and then take a photo or scan it and then submit it on Canvas. That's correct. If you want to print it out, that's fine. That's what most people did last semester. Most people just printed it out on paper and then completed the test and then scan it. I prefer PDFs if possible. You know, it's a little easier to print out for me as well. Okay, sure.
Okay, thank you.
Okay, yeah, no problem. You're welcome.